Yeah, so good morning, everybody. I think we can start now. Can you hear me well? And you can see my screen? Hello? Can you hear me and you can see the screen? Okay. Okay, thanks so much. So what I did last time, or what I did so far, I explained two different routing protocols. One is called link state, okay, and the other one is called distance vector, okay. Just I'm gonna make a very quick revision. As I told you, here's the idea of number one, both of them are doing the same thing. So both of them are gonna calculate routing table, okay? And this routing table is actually, it has the short or the least cost routes, okay? For example, here, as I told you, if you wanna transmit data from U to X, so it's gonna have the least cost routes, okay? But the main difference between the two protocols is actually the information every router has to share with other routers. This is the main difference, okay? Here in link state, I told you, you have to share the state of the links, okay? The state of, the state of the links, you have to broadcast it to everybody. So for example, here node A has to broadcast to everybody. My neighbor is P and F and E, and the cost is 134, whatever the cost is. And then everyone has to create what we call link state database. This link state database has every information here. So these are, this message here is coming from node A. This one is coming from node B, node C, and so on. That's why here I told you, and you have to broadcast. Broadcast means you have to send this information to everybody, so that everybody should have the same database. And then after that, you can run the algorithm, and then after that you can create the routing table. Okay. If we talk about the second one, distance vector, the story is completely different. Okay. Number one, that's why here we say here in link state, you can know the complete topology. So here you can know the complete topology. That means, what this means? It means if I want to forward a message from U to Z, I know the complete path. I can know that this path has X and Y. Okay, so I can know the complete topology here. The other one is different. The other one doesn't have the complete topology in distance vector. In distance vector, as I told you, all what you have to do is that, as I explained last time, for example, here, U is going to receive, node U is going to receive from its neighbors, from its direct neighbors, is going to receive what we call distance vector. And then, so this distance vector is actually going to tell the cost, for example, from V to everybody else, okay? The cost from X to everybody else, the cost from W to everybody else, without too much details. You don't need, I don't know the whole base. I just know the cost, okay? For example, it's very simple example here, as I explained last time. I can know, for example, if I want to send data to router Z, my neighbor V told me the cost is 5. My neighbor X told me the cost is 3. My neighbor W told me the cost is 3. Okay, so now if I wanna, here I'm talking about router U. So router U, if I wanna transmit data to Z, I have my 3 neighbors give me 3 options, or these options here. Okay. And then after that, I'm going to see which neighbor is better for me. So I have to add the cost here, this cost to reach to the neighbor, like 2 and 5 and 1. And then I'm going to take the smallest one. So, so number one here, the big difference between this one and the previous one is, in the previous one, you have to broadcast the information. You have to send to everybody. Here, you don't broadcast. Here, every information, you only transmit to your neighbors, only neighbors. This is number one. Is that okay? Number 2 here, you don't know the whole topology. Just my neighbor told me I can deliver message to X, to for example to Z, and the cost is 3. That's all what I know. How it will do that? What is the route? I don't know the complete route. Okay. Anyway, so I explained it last time. I explained how it works. So, and also very important to understand the idea of it may take several rounds It may take several rounds until you calculate the routing table. That's simply because think about how it works. Okay, every time there is a change in my distance vector, I need to tell my neighbors. Okay, and then my neighbors are gonna update their tables, and if there is a change in their tables, they have to tell their neighbors. You got what I'm saying? So there may be several rounds. If there is no change, okay, so I'm not gonna send any information to any update to my neighbors. Okay, that's why here we have what we call last time convergence. Conversion here means how many rounds it need until you finish the table, because if my distance vector change, this may trigger a change in other routers as well. This is because when I calculate my table, I need the information, or I need the tables of my neighbors, right? And use it to create my table. Okay, that's why it's very desirable to have fast conversion. Fast conversion means, look here, we changed one message, second message, okay, I'm done. Only in 2 messages. This is fast, right? Sometimes it needs to exchange so many messages here. So you change this one, you send to me, this trigger another change here, I transmit to trigger a change, you send to someone else, and so on. So it's gonna trigger several rounds here. In this case, we call it slow convergence. Okay. Anyway. Also, last time I explained to you one problem here. It's called the count to infinity problem. This is one of the problems we have in distance vector protocols, and I'm going to explain it again. Also, I'm going to tell you how we can solve it. But at least you should know. You should if I bring this one in exams. Number one, I'm going to ask you what is this problem. Okay, this number one. Number two, you should understand what is the reason for this problem and why you don't have this problem in link state. And how can we fix it? That's all what I need from you. But anyway, so let's see what is the problem. For example, if you look at the routing table here of y, if I want to send to x, I have 2 options, either via x here from y to x. Okay, so I can transmit to x directly, and the cost is 4. This is the first option we have here. Okay, the second option is, okay, and this is somehow weird, or this is the source of the problem. What happens is that y is going to tell its neighbor, I have a route to x and the cost is 4. Y is going to tell z, I can deliver message to x and the cost is 4. Okay, so what's going to happen? Z, so now z is going to say yes, yeah. So as you see here, this is the table of z. Z is going to say yes. I can reach to x through y, okay, and the cost is going to be 5. 5 is actually this one plus the 4 coming to me from y. Is that okay? The problem happens here right now. So for y, I received a message from z telling me I can go to x, okay, and the cost for that is 5. Okay, so that means one of the options for y is actually I can send to z, and z is going to send to x, okay, to x, which is 5. 1 plus 1 plus 5, that's why I have 6 here. Okay, let me say it again simply. Z have an option to deliver message to x, okay, through y, and this cost is actually 5. So if I use the same protocol without any modification, if I use the same protocol I have right now without any modification, this is exactly what can happen. From y to x, okay, I have one option which is 4, and that's why you can see 4 here. Okay, I have another option which is 6. How you came up with this 6? Yes, I have one here, and z is telling me it can send a message with the cost of 5. Okay, it looks funny. Why it looks funny? Because this 6, it looks funny, and actually it's going to create a problem right now. I'm going to tell you what kind of problem. Because actually here you are going to send to z, and z told me it has a path. Okay, but I don't know, because you don't give me any topology information. I don't know that this path is going to go through me back again. Okay, so that it's funny because here in this path, which is number 6, which has 6 here, you send to z. This is going to send back to you to send to x. You got what I'm saying? That's why you call it a reverse path. I send to you, you send back to me. You get what I'm saying? So, okay, that's what we call reverse base. If you have a reverse base, something like that, okay, if y select z, I think there is a typo here. This one should be, this is the problem. Y, okay, let me come. Y select this z as a next hub to x, but the path from z to x already has y. You got what I'm saying? So here y is going to select z to deliver message to x, but this path from z, it has y, and I'm not aware of that, okay, because you didn't send me the topology. A link state, because I already have information about the topology, I can easily find a problem like this one because I know the complete path. But here I don't know the complete path. You just tell me I can transmit messages to x and the cost is 5. You know, you got what I'm saying? So if this is through me, so I'm gonna have here what we call reverse base. You send to me, I send to y, and then y you send to x. Okay. So you are telling me this can create a problem. What kind of problem it create here? This problem actually we call it count to infinity problem. Okay. How this works? So it or how this happens? Okay. So here. Okay. So now I have here, as I told you, originally initially, we have here two options. I can go through 4, or I can go this space here from here to here, and this will be 6. That's why you can see here 4 and 6. Is that okay? In the very beginning. Okay. The very beginning, 4 is less than 6. Okay. Well, we don't have a problem here. We don't have a problem. I'm going to select 4, right? And we don't have a problem. The problem is going to happen right now. For example, if this 4 is changed to 60, as you see here, change it to 6. In this case, I'm gonna move to the next one. I'm gonna use 6 because 6 is smaller than 60. So in this case, I'm gonna use the reversed base. So here I'm gonna move to this space, and this space, as I told you, has the following problem. Okay, count to infinity. Okay, so let me tell you what I mean exactly. Okay, so what happens is that z is telling me is z to y. Z is telling y I can reach to x. So I can go to x, and the cost is actually, originally it was 5, okay? And then actually y is telling to z, I can reach, y is telling z, I can reach to x, and actually the cost is originally was 4, okay? This was originally, okay? So now what happens here, y is gonna use this route, okay? It's gonna use this route. So I change this one to 60. So now I'm going to select this one to this route. So the problem happens here, okay? Because here I'm gonna tell z, okay? Already I have 5 here, right? So I'm gonna add 1. It's 6. So I'm gonna send this information to z. I'm gonna tell z, okay, z. Now there is a change. I can reach to x, and the cost is 6. Instead of 4, now it is 6. Okay. And now, because z is using this one here to reach to x. Okay. So here I'm gonna update this one. So now you are telling me y is telling me now the cost became 6, right? So I'm gonna add this one to go to x through y, I have to add 1. That's what happened here. Then you have to send it back to y again, okay? Because y is using this one to reach to x, okay? So you are telling me my z is telling to y, my route to x, it changed from 7 to 8, right? From 6 to 7. So you add 1 here to become 8. Okay, and then you tell the other one here, now this 8 becomes 9. So actually what happens, because the route here from z is gonna go through y, every time there is a change from y, so here when this one when z change, y has to change, because y is gonna use the value of z is gonna use the value given to it from y, right? So this will continue until here we'll call it infinity, but actually it's not going to be infinity. Okay, I'm going to tell you what happens here. So this one will continue here. You change it to 6, you change it, I change it to 7, and then I sent it to you back, because you are going to use this one to route back is to X. You are going to increment it, you change it, it's going to continue this way 50 iteration until what happens here is that until this one here becomes, until this value will be 51. Once this one becomes 51, so I'm gonna move to this route. I'm gonna select this route instead, because this route is smaller. You got what I'm saying? So again, I just, it's maybe difficult to explain, difficult to imagine, but the problem happens simply because we don't send topology information here. So what happens here, you reverse base. This is a problem, reverse base. So that's why if there is a change in one path, you are going to trigger another change, another change. It's going to continue this way, because the path, you are telling me the best to Y change it. Okay, so, and you are using my path, okay, to X, right? So that's why when I change here my cost to X, and Y is also using me to forward to X, any change here is going to trigger a change here. A change here, trigger change here. Change here, trigger a change here. We're going to continue this way. It's going to take very long time, very slow conversion. This is a problem here. So the problem is because of this reversed path, because the current, based on what I explained right now, and this is a basic idea of this protocol, it's going to allow something like that. Okay. And this is going to create very slow convergence. Okay, so it's going to take some time until, especially if there is a failure, link failure. For example, you know, if there is a link failure, this number will be very high, very large number, and this will trigger. For example, here, this one was 4, and because of failure, something like that, this one increased to 60. For example, big jump from 4 to 60, because this will take a lot of time here until you reach to conversions. Okay, so the question is that now, how we can solve this problem? Okay, solving this problem, you can simply prevent any reverse base, because simply it doesn't make sense. You send to me and then I send back to you to forward to Y. It doesn't make sense at all to do something like that. That is why this can be handled by Z. Once Z finds something like that, it has to notify Y we need to cancel this space. This shouldn't be an option here. The reverse batch should not be an option. We shouldn't use it. Okay, you know how we're gonna do this? Okay, once Z find the reverse path. Okay, reverse path means if you wanna reverse path. So okay, let me tell you what is the problem. The problem here, Y is gonna tell me I have a route of 4, okay, to X. Okay, so what should happen here? I should not tell Y I have route to X, which is 5, simply because I'm going to use Y. This is going to create a reverse path, right? And that's what happened here. So if Z finds something like that, I'm going to create what I'm going to advertise to Y is already going to go through Y. If I have a case like this one, I'm not going to send the cost of 5. Instead, I'm going to send the cost of infinity, so that you are not, we can avoid this. Infinity here means you should not use this path. You should not use it. That means I need to modify the basic protocol I explained here. The basic protocol I explained here is, once you create the distance vector, for example, we have here E has neighbors A, B, and D. Okay, so once I create the distance vector, I have to broadcast it to my neighbors. So E has to send to D. Also, E has to send to B. It's the same information. I have to send it to A. It's the same vector, same information. Okay, but now it's not going to be this way. If I want to fix the problem, if I find the reverse path, for example here, so I'm going to put here infinity. and then everything else will be the same, but I'm gonna just put here infinity so that you don't use this path. And then I'm gonna send this one, for example, to one node, the node that has a reversed path. But the other node, I'm gonna send the correct one. You got what I'm saying? So that means, let me say it in a different way. That means I can reach to X through Y, and the cost is 5. This is one information. I have to give this information to anybody else other than Y. Anybody else other than Y, right? For Y, I'm going to tell Y, actually the cost, if I want to go to X, the cost will be infinity, right? Why? Because I want to prevent Y from sending to me and then sending back to Y. See? So this is, and I'm going to show you right now, if this one is infinity, as I have just told you right now, so that means convergence is going to be very fast. So what I'm saying here, you should understand what is the problem. You should understand how we are going to do little modification on the basic idea for this protocol, as I explained before, to avoid this problem. So you can see here right now, I told you I'm going to put here infinity. So what's going to happen here now? Originally it was 4. Is that okay? And now 4 it changed to 60. Okay, so 4 now becomes 60, right? But because 60 is still better than infinity, I'm going to continue here, right? What happened to before, it was actually 60 and this one was 6. That's why I moved from here to here, and this created the very slow convergence, okay? But still, I'm going to keep, this one is still 60, so I'm going to broadcast the 60 here. So I'm going to tell here Y is telling to Z, I can reach to X, and the cost now is 60, right? So 60 plus 1, so this one should be this one should be 61, as you see here, but I have a better value, which is 50. So so now I'm gonna move from 60. Originally it was 5, right? Originally when it was 4 and 1, this one was 5 originally. Okay, so let me explain it better. So originally Z has 2 options, either 50 as you see here, or 5 this way, because 5 is smaller than 50, so I'm going to use 5. But now 5 it changed to 61. 60 here plus 1, 61. So in this case, I'm going to move quickly. I'm going to move to this link quickly, right? So then I'm gonna broadcast this link. I'm gonna broadcast this link to Y. So now Y is gonna move to 51. So now Y, if Y wanna reach to X, has to go through this way instead of this way. Okay. So now I'm gonna still tell X. Now the distance vector to X, I'm gonna tell Y. Z is gonna tell Y. The distance vector to X now it changed it. Okay, and now it is 50. Okay, so now you update it to 51, and then everything is already stabilized. So again, it's going to be much better than what we have done here. So this is actually what. So again, the main problem here, we have reversed path. Reversed path means you send to me, and then I give you back to you to send to X. Okay, and this something has to be handled by Z. So this solution, we call it Poisson reverse. It's like you are poisoning the reverse. How can you poison the reverse? I told you, when I sent my distance vector to Y, if this distance vector is going to create the reverse path, I'm going to make the cost infinity. Okay, instead of, it's actually 4 plus 1. 4 plus 1 is 5 plus 1. Instead of making 6, I'm going to make it. This is what we call Poisson reverse. Is that okay? Any questions? Okay. So the question is that, again, this is difficult to problem somehow, because here I'm giving you a very small example. If we have only 3 routers, okay, maybe the problem is going to be, we can have the same problem if we have, like, for example, several routers are connected together. Maybe the problem is going to be more complicated, because it may take several rounds here circulating here until convergence happen. So here, maybe on the smallest scale, if you have something like that, it would be easy, but on larger scale, so that's why, in addition to Poisson reverse, maybe we need another way to solve it. Okay, the other way is here, we should try we should try avoid using large numbers here. Okay, for example, if there is a failure in this link, I can use a small number, as you will see later in one of the practical protocols used. I'm going to use, for example, number 15. So 15 is like infinity. This is the maximum number you can reach. You got what I'm saying? That even if you have slow convergence, you are not gonna count to 1,000 or a very big number. No, once you reach to 15, that means it is infinity. You understand what I'm saying? That means if you can find the cost of a path of 15, so 15 for you means infinity, means unreachable. This means you should not. Look, that's exactly what happened here. What happened here? I continued counting 6, and then you change to 7. I sent 7. Now you can find the new path is 8. But then it is 9 and 10. You are gonna continue this way until it is 50 or 51 greater than this one. Once this one is greater than this one, I'm gonna change from here. I'm gonna move this way. So if you can use smaller numbers, okay, this will be much better. I'm not gonna count for a very long number. Okay, that's why you can see in one of the practical protocols I'm gonna explain. They set this metric to only 15. So 15 means infinity, means they are not connected. Okay, so if you keep counting this way until 15. So I'm going to stop at 15 because it means that it's not reachable, something like that. Okay. One of also the things here we have in routing protocols, sometimes we have loops in routing protocols. So here loops means if you have here multiple routers this way, maybe when you transmit a message here, this message is gonna circulate for a very long time. Okay, without reaching to its destination. Okay, this may be for several reasons. It can be because of the slow convergence. Remember the problem of the slow convergence, the routing tables are not true, are not finalized yet. So if you use these routing tables for forwarding messages, you can have some kind like a loop. Also because of incorrect configuration or something like that. So it may happen that I have one packet, and because we have some issue or problem in the routing, this packet is going to be circulate for a very long time. Okay, and it will never reach to the destination, or it's going to reach the destination after a very long time. So what's the problem here? Such a packet is going to consume too much bandwidth. That's why in most of the protocols, in every packet they put something we call time to live. Okay, for example, if I say time to live is 13, that means every time I forward a packet, I'm going to reduce this one by 1. That means we should not forward the packet more than 13. Okay, once it is 13, I'm going to drop it. Okay, again, let me summarize what I said. Sometimes one packet is circulating because of routing problems, is going to circulate between the routers, okay, for a very long time. Okay, again, this is because of slow conversion, because of problems in the router. That's why we put a limit here. Usually in the packets, we put a limit. For sure, the problem here, you consume a lot of resources, right? We put a limit. Okay, this limit, that means the package, any package should not be forward more than this number. If we have a loop, if we have a problem and we have loops, and this, if I keep relaying this message, every time I'm going to reduce this number. So originally it's going to be 13. Once I relay one time, it is 12. Once I relay, it's 11. It is 10. Once it is 0 and it has not been delivered to the destination, it is 0, I'm going to drop it. It shouldn't continue in the system, just circulating in the system and consume a lot of bandwidth. Okay. Finally, here I want to make a comparison between LS and GV. Okay. So let's talk about complexity first. In complexity first, as I told you before, in LS we have actually the entire topology. Okay, that's what I told you. Okay, but in distance vector, you only have a distance vector from neighbors. Okay, here in LS, you send information about your neighbor to everybody. So you have a small message, but you have to broadcast to everybody in LS. In GV, no, you have to transmit everything you know, okay, but you have to transmit only to your neighbors. only to neighbors. Here you have to transmit to everybody, okay? If you talk about convergence, a distance vector protocol is actually slow, LS is fast, okay? Before I continue, in conclusion, the two protocols are used in practically, as I'm going to explain later. So I'm going to jump here. I'm going to tell you in the last section here, routing the internet, I'm going to explain real practical protocols used in the internet. One is called RIP, OSPF, and BGP. Okay, you can find here one of them is using LS, the other one is using DV. Okay, so you will see. So that's what I want to tell you. Both of them are used, right? Because everyone has strengths and weaknesses. So it's not like one of them is always better than the other. No, all of them are used. Okay, so here also you can see here, if you talk about resources, LS needs more memory because you have to create, as I told you before, you have to create the database here. You need to receive a lot of information, a linked state database. You have to create this one, and you have to run the algorithm based on these values. But the other one is much simpler. It's somehow the comparison is really tricky. I'm going to tell you why. Because here, this one is just very simple. As I told you before, all what I'm going to do, I'm going to receive numbers, distance vector from my neighbors. I'm going to add the cost here. I'm going to add the cost, and then I'm going to select one of them. It looks very easy. However, you need to do it multiple times. You may need to have several rounds. That's why the comparison here somehow it's tricky. Okay, but in general, LS needs more memory to store the data received from everywhere in the network. Also, it needs CPU processing because you have to run every node has to run the complete protocol. Okay. Okay. Sorry, give me just 1 second. Okay, so yeah, so in general, this one needs more memory and more CPU processing. The last thing here, I think they have a question. Oh, there is no sound. Hello? No, I think you should hear me. Is there a sound? You can hear me well now, right? Hello? Can you please write if you can hear me or not?
Yes, doctor.
Yeah, you can hear me, right? Okay, anyway. So if you don't hear me, so you have a problem in the speaker. So anyway, so now let's move to the last one here. What about robustness? Robustness here means, what about if there is a router fails? What about if router misbehaves? What do you mean by router misbehave? It means this router intentionally sent, for example, wrong information. Okay, so let's see which one can do better regarding robustness. There is one advantages in LS comparing to DV. In LS, I know the complete topology, so I have different. This is maybe an advantage here. So, for example, if I come here, as I told you before, for example, if you see here, if I want to go to W, if I want to go W, actually I have different options here. I have different option, but for sure I'm going to select the smallest option through Y. So here, if I want to go to W, so for example, if I go through this way, Okay, this will be the cheapest one, the best one. But I have other options. Okay, so for example, here I can go this way 5. So I already know all the options I have. I can go this way as well, this way here. So I can know all the options I have. Okay, but anyway, so and you know the complete topology. That means if a router fail, I can transmit the packet to other route. So because you know the whole route, if I notice, for example, every time I use this route, there is the packets are not delivered, I can switch to another one. So this gives some kind of robustness. I don't have this option in the other one because you don't give me topology. You can just so I don't know the complete path. Maybe here also in distance vector, what happens here, incorrect calculation can propagate. You know why? I'm going to tell you why. Because the way we calculate the routing table in GVE is every node has to transmit the distance vector. And based on these values, so based on your routing tables, I'm going to create my own routing table. So if you do miscalculation and you send the wrong distance vector here, I'm going to, this will propagate. The error will come to me, right? So if you calculate the cost inaccurately, so I'm gonna use it in my routing table and maybe propagate to someone else because my routing table is computed based on that. Maybe the comparison is these are, again, the conclusion is that both of them are okay, both of them are used, but regarding convergence, DV is slower than LS. Complexity, one of them knows the whole topology, the other one only, one of them transmit message to broadcast to everybody, some one of them only transmit to neighbors, and so on. Okay. So now I'm going to move to next section about hierarchical routing. So the important question I need to answer right now, okay, you already explained to us, if I have a network like this one, if I have a network, something like this one, how I can create the routing table. So now the question is that how I'm going to use these two routing protocols in the internet. Okay, in the internet we have millions of routers. So are you going to make it this way? You are going to have millions of routers. We're gonna make it this way. We're get all the routers in the world. I'm going to put them together, and then I'm going to run one of these protocols. The answer for sure no. If imagine scalability is not good at all here. So imagine, for example, here I give you one example. Here we have here in this example we have just 4 or 5 routers. Imagine we have millions of routers. Imagine how the calculations are going to be difficult, the transmission is going to be difficult. So we're not going to use it this way. I'm going to tell you how in the internet because of the scalability. So I can say, so these protocols, we can use them, but when the network is small, when it is big, it's not a scale. It's going to be, you can use them, but it's not going to be efficient because you have to transmit a lot of messages. It's going to take competition. It's going to take a lot of time and so on. So that's why in the internet, and I told you the main problem in the internet is scalability, right? So that's why in the internet we have what we call hierarchical routing. I'm going to tell you what it means, and it's not very far from what I explained before. So as I told you before, the internet is actually a network of networks, as I told you before. So for example, we have here one network, okay? And inside this network, we have what we call sub-network. This network is under the administration of only one party, like for example, Qatar University or something like that, okay? And then we have another, and here this network, here in this section, we're gonna call it AS, autonomous system. So we call it like autonomous system. It's a network under the administration. And then we have here at the border router, these border routers are used to connect different AS together. Is that okay? We need to connect the different. So here we have AS1, AS2, AS3, AS4. 4. So this is not far from what I explained to you before. It's network of networks. Okay. So now the new part I'm going to explain right now is routing. Now we need 2 different types of routing protocols. Okay. Number 1, we need routing protocol here if I want to transmit a message inside the same AS. So I need a routing table to tell me if you want to go to the host X, how I can forward here inside AS. And this routing protocol actually is called intra-routing protocol. Intra means inside the AS. So here we need two types of routing protocols. The first one here, we call it intra AS routing protocol, or sometimes we call it interior gateway protocol. Okay, we need another routing protocol, we call it inter routing protocol or exterior routing protocol. The first one here is used inside if you want to transmit its routing information inside the AS. But here between the boundary here, we need another routing protocol to connect. If you want to transmit outside this AS, we call it inter-routing protocol, okay? So for example, I want to transmit here, I want to transmit from AS1 to AS, for example, 3 here. So I'm going to transmit to this router. This router should have information, how it has to forward it, so that it's going to go to AS3, okay? So that's what I'm telling you. So now I'm telling you, practically, we use two different types of protocols. One inside AS to give you how can we deliver message inside AS, if every AS. Also, we have another level of routing protocol. We call it inter-routing protocol. This one is actually how can we connect the different AS together. Okay. In other words, if I want to deliver a message from AS1 to AS for any another AS. Okay. So here the border routers should have information about how can we deliver, how this message has to be forwarded here between. So that's why we have two levels. One level should give you information about the delivery of message inside the AS. Another one give you information about the delivery of message between the different AS here. Okay. That's what I'm saying here. We create, if you want to create just a flat network without hierarchy, it's not scalable. How can we have, if we have 200 million destination, how can you create routing? How can you run LS or DV in this case? Okay, so that's why, as I told you before, we are going to have hierarchy, network of networks, as I told you before. But now regarding routing, we're going to have two different routing protocols. So as you see here, this is one autonomous system or network. Inside the network here, we have what we call intra-AS. So this intra-AS is actually going to take care of, is going to give you information about how can you deliver messages between computers inside the AS. Is that okay? We have another one here. That's actually here. Is this what the inter here? If you want, how can we connect the different AS together using the border routers here, border routers? Okay. So, and now I want to tell you also something interesting. So now I told you here we have here border router. Okay, and we agree now we have two routing protocols. Okay. So we have here a border router is connected to another border routers, and so on. Okay. So here, this one needs information from the intra-routing protocols. Okay. So that if I want to transmit a message from one AS to another AS, I should know how to forward this message. Should I send it here to go to this AS, or it has to, for example, it has to go this way? I should have information from intra. Is that okay? But also, this border router also need to know information about, sorry, I'm really sorry. This is called inter. So inter is actually between the different AS. Intra is inside the AS. Also, this router, because it may happen that I receive a message and I want to deliver this message inside the AS. Is that okay? So in this case, also I need to have information. My routing table here should have information about how can you deliver message inside here. That's why if you look at the routing table of this one, of the router here, the routing table has two parts. One part is coming from the inter, okay, and this one I'm going to use it if I want to deliver message outside the AS. Also, one part here is coming from the intra routing protocol, so that, and this one I'm going to use it if I want to deliver a message inside the AS. You got what I'm saying? So that's why I think I have a very nice, that's why I have a very nice figure here to tell you in this figure. So this is the routing table here actually has two parts. That's what I want to tell you here. One part is coming from intra, one part is coming from inter. I'm going to use the intra part, is the information coming to intra to when I deliver a message from one ES to any other ES, another ES. I'm going to use this information here. But also I need information from inter so that when I receive a message and this message I have to deliver inside my ES, so I have to transmit inside ES. Is that okay? Okay. One of also one, this is for the border routers. What about the internal routers? Okay, here just to make it simple, I just give you one simple case. I told you we have here one border router. If I wanna here internal, if I have internal router here, if I for sure I have information from the intra, so I'm capable to transmit to deliver any messages inside the ES. If something, if I have a message outside ES, I have to send to the router, to the border router to take care of it. That's what I told you. I just try to make it simple. So in this simple idea, I don't need to know anything from inter. So I didn't anything anything outside ES, I'm gonna send to the border router is gonna take care of it. Is that okay? So I don't need to know any information from the inter. I didn't need to know any information about the other ES. Okay, but again, this is just a very special case. This is just a very simple example. In reality, this is not the case. In reality is, for example, here I may not have only one border router. Okay, for example, here I have a border router and this is connected to AS1. Okay, and I have another one here connected to AS2. Okay, but there may be another border router here. So in reality, there may be more than one border router. Is that okay? So that means, and here we have AS7, maybe here also, and so on. Okay, that means for the internal router, if I want to transmit something outside the ES, I should have some information so that I have to know, for example, if this is ES3, for example, okay, and we have ES7 here. If my destination is in ES3, so I have to transmit to this border router. If it is in ES7, so I have to transmit to this one. You got what I'm saying? So in this case, it is not enough to have information only from intra, right? I have to get some information related to which router, border router I have to select if I want to transmit outside the ES. And this is actually information is given from inter, right? So also it still needs some information from inter routing protocols, okay? And yeah, that's what I'm explaining here. For example, yeah, for example, here we have 1G. This internal router here, if I want to transmit something, is going to go to ES2, so I have to send it to this border. We have border router here, we have another border router here. If I want to transmit something to ES3 or something to X, so I have to transmit to 1C. You get what I'm saying? So that means I need to get some information from inter as well to help me to know where I have, if the packet is going to go outside, which router I have to transmit to. Is that okay? Again, so conclusion here, what I did so far, I explained to two routing protocols. I told you in the internet, because it's very scalable, I can't just create one network and use one of these routing protocols. This will be unacceptable simply because it's going to be huge network. That's why we have the idea of hierarchy, and then you will see what we are using them, but we are using them in small scale. You got what I'm saying? For example, inside ES, I can use one of these two inside ES. Even inside ES itself, if the autonomous system or the network is a huge network, maybe in one building or in one sub network, I can use one of these protocols. Okay, so in the last part here, in the last part of this chapter, I'm gonna give you information about real protocols used in the we use them in the internet. Okay, the tick is they don't have technical part. So the technical part, I already finished the technical part. I just want to describe to you some of the protocols. I'm going to tell you if these protocols are using link state or distance vector. Okay. For example, here in this chapter, I'm gonna, in this section, for intra means again inside the autonomous system. What we can use routing information protocol RIP or OSPF. These are very widely used protocols. One of them using link states, the other one is using distance vector. Between to connect the different A's together, we have one is called border gateway protocols. So I'm going to explain them next time. Again, they don't have the technical part here. Nothing is new comparing to what I said before, but just I'm going to give you practical numbers. I'm going to give you some parameters. For example, here, every 30 seconds, I'm going to just describe these protocols. I'm going to describe what messages we have here and so on. But the technical part will be exactly the same thing as we did before. Okay. So anyway, so I'm going to handle this part next time. So let's take the attendance here. Okay, so it is 3097. Okay, 3097. So I'm very close to finish this chapter. Okay, sorry. Oh, what did I do? Yeah. So just I'm gonna explain these protocols next time. Also, we're gonna have a project presentation next week. We're gonna have quiz also next week. Okay, and the last week I was told the last week there should be no lectures in the last week because you have lab exams. So we should finish everything by next week. Okay, including
Victor?
Yes, sure.
The quiz will be the whole chapter of 7 or part 1 or 2?
Okay, let me think about it and I'm gonna tell you. Maybe I'm gonna send to email to you today also. Okay, because
okay, inshallah.
inshallah. It can be until here, until distance vector protocol, link and distance vector. Is that okay? Because you need
Yes.
to start chapter 7 anyway. So from the beginning until here. Okay.
Okay.
And maybe is you want to take it on what date? Sunday, Tuesday, or Thursday? Make it Thursday to give you more time.
Yes, it's better.
Okay, make it Thursday. Okay.
Thank you.
During the lecture, yes, Thursday is okay. Just to give you more time. That's okay. Okay. Okay, I think that's everything. But I'm gonna send you the schedule for presentation to make presentation next week. Okay. Thanks. Bye.